Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is why start delta run reduced voltage starters. Our objective is to introduce the why start delta run reduced voltage starting method. Reduced voltage starting methods reduce inrush current and modify acceleration and starting torque characteristics. This lecture operates under the assumption you've watched the primary resistor reduced voltage starters and motor connection diagrams lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. As you're no doubt sick of me reminding you, the direct and instantaneous application of full voltage to a motor at standstill produces a tremendous surge of current known as inrush. Although brief, inrush can place an unnecessarily high demand on the electrical distribution network, and industries often pay a financial penalty for such events. Additionally, the abrupt acceleration of a motor from standstill may damage the mechanical linkages, like belts, chains, shafts, gears, and couplings the system uses to manipulate the applied load. It is for this reason reduced voltage starting methods are employed. Reduced voltage starting methods include, but are not limited to, primary resistors, part winding, Y-start delta run, soft starters, and motor drives. All these methods serve to limit inrush current and reduce mechanical stresses to the driven load. Today we'll discuss one of these methods, Y-start delta run reduced voltage starters, also called star delta starters on an introductory level. After we've discussed timer relays, expect to revisit reduced voltage starters incorporating timers in later lectures. As you'll soon learn, the term reduced voltage relies upon some mathematical trickery. However, the effects are the same. When this technique is employed, a motor experiences less of an inrush and accelerates gently in comparison to a full voltage starter. As the title implies, Y-start delta run reduced voltage starters use a Y configuration when starting a motor and a delta configuration in run mode. This implies that motors making use of this technique must be able to be placed in either Y or delta configuration. This rules out all 3-lead and 9-lead motors, since these motors are pre-configured by the manufacturer in an unalterable Y or delta configuration. Eligible for this technique are 6 and 12-lead motors. The commonality exhibited by these motors is that they are customizable and can be placed in either Y or delta configurations because both ends of all windings are accessible. The mathematical trickery surrounding a Y-start delta run reduced voltage starter stems from a property inherent to industrial three-phase AC distribution networks. Recall that three-phase AC is characterized by 3 AC waveforms with identical magnitude and frequency, however, temporally offset from each other by a phase shift of 120 degrees. This 120-degree phase shift means at any given time there is not only a voltage differential from a particular phase to neutral, but also a voltage differential between phases. This relationship is such that the line-to-line difference RMS value is always square root 3, or 1.73 times, greater than line-to-neutral RMS value. The 3 line-to-neutral voltages are phase-shifted 120 degrees with respect to each other, as are the 3 line-to-line voltages. Consider a light industrial 3-phase AC system characterized by a 120-volt line-to-neutral and 208-volt line-to-line values. If this motor was placed in a Y configuration, each winding would experience the comparatively smaller line-to-neutral value of 120 volts RMS. If, however, this motor was placed in a delta configuration, each winding would experience the comparatively larger line-to-line value of 208 volts RMS. Herein lies the mathematical trickery of the Y-start delta run reduced voltage starter method. Although the system voltage remains constant, the different configurations see different aspects of the same system voltage. The Y configuration sees the comparatively smaller line-to-neutral voltage, and the delta configuration sees the comparatively larger line-to-line voltage. Given voltage is the cause of current, a motor started in the Y configuration would therefore draw less current than one started in the delta configuration given identical windings. The Y-start delta run reduced voltage starting method takes advantage of this by starting a motor in a Y configuration, and then, once the motor is accelerated for a predetermined period, the Y configuration is momentarily broken and then reconfigured as a delta. Each winding now experiences the larger line-to-line voltage. However, given the motor is not at rest, but rather already moving, the inrush current will not be as great. The Y-start delta run reduced voltage starting method therefore serves to stepwise limit the inrush and mechanical stresses of the driven load. This technique need not be limited to just 6-lead motors. Consider a 12-lead motor necessitating connection to a low voltage source. Winding A1 is in parallel with winding A2, and similarly, B1 is in parallel with B2, and C1 is in parallel with C2. These parallel configurations can be placed in a Y configuration to start, using the comparatively lower line-to-neutral voltage, and then disconnected and reconfigured in a delta configuration to run using the comparatively higher line-to-line voltage. Similarly, consider a 12-lead motor necessitating connection to a high-voltage source. Winding A1 is in series with winding A2, B1 is in series with B2, and C1 is in series with C2. These series configurations can be placed in a Y configuration to start using the comparatively lower line-to-neutral voltage, and then disconnected and reconfigured in a delta configuration to run using the comparatively higher line-to-line voltage. Regardless, the switch from Y configuration to delta configuration uses different aspects of the same system voltage, and as a result, inrush current and mechanical stress is reduced. Notice the graph of inrush current for the Y-start delta run reduced voltage starter method shows a transient spike, characteristic of an open transition reduced voltage starter. As you recall from our preliminary discussion on this topic, an open transition reduced voltage starter briefly de-energizes the motor during a transition from start to run mode. The transition time between the Y configuration and delta configuration requires a measurable amount of time to take place due to the electromechanical nature of the switching apparatus, and this spike is a product of the open transition period. We'll discuss solid-state devices without moving parts, in later lectures that minimize transition states and transient events. Recall the timing of the transition from the Y-start to delta run mode affects the inrush current graph. Notice if the transition from the start to run takes place quickly, the motor is only given a short time to accelerate. Inrush current will be more. If, however, the transition from start to run mode takes place later, the motor is given more time to accelerate. Inrush current will be less. Thus far, we've examined only elemental diagrams of Y-start delta run reduced voltage starters in the most nebulous of terms. Let's take a look at a primary schematic making use of 3 contactors, S for start, R for run, and Y, obviously for Y, that selectively connect the windings in a Y or delta configuration. We'll be making use of a 6-lead motor, where winding A has terminals 1 and 4, winding B has terminals 2 and 5, and winding C has terminals 3 and 6. This Y-start delta run reduced voltage starter can be summarized as 2 distinct stages. The start stage sees the closure of both the S and the Y contactor. The run stage is characterized by the closure of both the S and R contactor. It should be readily apparent that the simultaneous closure of the Y and R contactor is something to be avoided at all costs, since it would constitute a shorting of all 3 phases and a phase-to-phase event characterized by an arc flash hotter than the sun. For this reason, the Y and R contactors are electrically and mechanically interlocked, as we'll later learn, to prevent this occurrence. Either the Y or R are closed, never both at the same time. When the Y contactor closes, it joins terminals 4, 5, and 6 as the central node of a Y configuration. Note the Y contactor has no overload contacts, since it only serves to connect the central node. With the Y contactor closed, the closure of the S contactor connects this motor to primary voltage in a Y configuration such that windings A, B, and C experience the comparatively lower line to neutral voltage. Winding A receives phase L1, winding B receives phase L2, and winding C receives phase L3. Given voltage is comparatively less, the motor experiences comparatively less inrush current and begins to accelerate. Note that the S contactor does have overloads in series with it, since it is delivering current to a motor. When the Y contactor opens, it breaks the Y configuration, and primary current would stop flowing. This is the open transition. Upon closure of the R contactor, winding A is connected line to line from L1 to L2. Winding B is connected line to line from L2 to L3. And winding C is connected line to line from L3 to L1. This already spinning motor is now in a delta configuration such that windings A, B, and C experience the comparatively higher line-to-line voltage. Note the R contactor doesn't necessitate an overload, since current through each winding will be experienced by the overload already in the circuit. Note the transition time between the opening of the Y contactor and the closure of the R contactor makes this an open transition reduced voltage starter, because the motor windings are momentarily de-energized during this period. This open transition can cause transient spikes, where magnitude is proportional to the degree of imbalance between the running motor and the primary voltage. Such disturbances can affect the supply and sensitive electrical equipment in the vicinity. Still, the staged reconfiguration of the motor windings yields less inrush and mechanical stress than a regular full voltage motor starter, even when the transient spike is taken into consideration. Note, the motor connection diagram must be adhered to such that both Y and delta configurations produce the same direction of rotation. If the delta configuration produced an opposite rotation, the motor would be plugged in reverse, counter to our intended purpose.